Hello, today we are going to discuss about energy band diagram of PN junction under open circuit, under forward bias and under reverse bias. And the important thing of this energy band diagram is nothing but we know every PN junction will be consisting of potential barrier, that is every potential barrier will be consisting of height as well as width. In general diagrams we can only show the width, we cannot show height. The height of potential barrier only find with the help of energy band diagram. So from the energy band diagram we will identify what is meant by actual meaning of height of potential barrier and how it is going to be reduces and how it is going to be increases. What happens when that happens we will see. Okay, so before going for the PN junction, we will remind the energy band diagram of p-type and n-type, because a PN junction is nothing but simply a combination of p and n-type materials. So we start from the energy band diagram of p-type, later n-type, then we will go for the open circuit PN junction. Okay, so let us start. Energy band diagram of p-type semiconductor. Energy band diagram of p-type semiconductor. A p-type semiconductor is going to be formed. A p-type semiconductor is formed whenever a trivalent impurities are added to the intrinsic semiconductor. So first we draw the intrinsic semiconductor energy band diagram. From that one we will draw the energy band diagram of p-type. So this is conduction band and it is valence band. EC, lowest energy level of conduction band. EV, highest energy level of conduction band, and the gap between EC and EV is nothing but energy gap, that is also called as forbidden band. Okay, and for intrinsic semiconductor there is a Fermi level, it is at the middle of energy gap, so it is indicated as EFI, intrinsic Fermi level. This intrinsic Fermi level indicates the comparison between number of free electrons present in the conduction band and number of holes present in the valence band. If it is in the middle, the meaning is nothing but number of free electrons in conduction band is same as number of holes in the valence band. So it moves towards either conduction band or valence band depending on which dominates over the other. Okay, so for intrinsic both are going to be same, that's why it is in the middle. And if you add trivalent impurities is nothing but which will have only 3 valence electrons. The examples of that one is nothing but aluminum, gallium, indium, which can have only 3 valence electrons, which can accept one extra electron such that it will get stable configuration. So by accepting an electron, there will be a hole created, so that number of holes will be increases. That number of holes is equal to the acceptor concentration for the p-type semiconductor. So that Fermi level moves towards valence band to indicate number of holes are more in p-type compared to number of free electrons in conduction band. So this is what you are going to get. So this is, we can say it as EFP, Fermi level of p-type semiconductor. Okay, so Fermi level of p-type semiconductor will be equal to EFI if no acceptor has been added. As the number of acceptors are going to be added more, at that time the Fermi level moves down. So this EFP is going to be related to NA, number of acceptors, and EFI is going to be related to Ni, intrinsic carrier concentration. Ec is going to be related to Nc, and Ev is going to be related to Nv, where Nc and Nv are going to be represents. Nc is nothing but effective number of energy levels present in the conduction band. Effective number of energy levels present in conduction band, whose the value is nothing but, the value is 4.82 into 10 power 15 into mn by m naught to the power of 3 by 2 into t power 3 by 2. Units are going to be per centimeter cube. Mn is nothing but effective mass of electron. M naught is nothing but rest mass of electron. Okay. Similarly, Nv can be written as, Nv is nothing but, Nv is effective number of energy levels present in valence band. So by that time the value can be written as 4.82 into 10 power 15 into mp divided by m naught, mp divided by m naught to the power of 3 by 2 into t power 3 by 2 per centimeter cube. That is, both the values are going to be approximately same except for Mn and Mp. If Mn is equal to Mp, at that time Nc will be equal to Nv, where Mp is nothing but effective mass of hole. M naught is again same as previous, that is rest mass of electron or true mass of electron. So, and for a p-type semiconductor, we can calculate the majority carrier concentration. Majority carrier concentration of p-type is nothing but hole concentration. Hole concentration. Hole concentration, number of holes present in unit volume. Hole concentration can be calculated. Hole concentration. This is going to be indicated as Pp. Pp, number of holes present in p-type, is approximately equal to number of acceptors you are adding. So this can be calculated. Pp is equal to Nv into e power minus of EFP minus EVP divided by KT. EFP, EVP, we are going for this one. The same ECEV can be written as, EC is nothing but ECP, since we are dealing with p-type. EV is nothing but EVP. Okay. So from this one, if you modify this equation, this Pp is approximately equal to, Pp is approximately equal to Na. So from this one you can write it as Na by Nv is equal to e power minus of EFP minus EVP divided by KT. Okay. So if you simplify this one, you are going to get this equation, EFP minus EVP is equal to KT natural logarithm of Nv divided by Na. This is very important equation. EFP minus EVP can be written as relative distance between the Fermi level of p-type and valence band edge. So EFP minus EVP is simply the relative distance. This is the relative distance between Fermi level of p-type and valence band edge. So KT natural logarithm of Nv by Na. Similarly, we can write the relative distance between any other two energy levels like this. We will see the energy difference between EFI minus EFP, that is relative distance between the intrinsic Fermi level and Fermi level of p-type. Okay. Otherwise, the relative distance of Fermi level with respect to intrinsic Fermi level also we can say. So EFI minus EVP can be written as KT natural logarithm. From the previous equation, if you observe, Okay, from the previous equation, if you observe, EFP is going to be related to Na. Na is going to be comes in the denominator. So first one is related to denominator, and second one EVP is related to NV, that is in the numerator. So here also numerator is nothing but this one, that is EFP, which is nothing but Na. Numerator is nothing but Na divided by EFI is nothing but Ni. You can write like this. EFI minus EFP is equal to KT natural logarithm of Na by Ni. This also you should remember. So similarly we can draw the n-type semiconductor energy band diagram. The n-type semiconductor energy band diagram is going to be, again we will start from the intrinsic semiconductor. So this is energy band diagram of intrinsic semiconductor EC, and it is for valence band EV. EC is nothing but lowest energy level of conduction band, EV is highest energy level of valence band. And for intrinsic semiconductor, the Fermi level will be in the middle, which indicates number of free electrons in the conduction band is same as number of holes present in valence band. But n-type semiconductor is formed by adding pentavalent impurities. Each pentavalent impurities can donate one free electron, so that number of free electrons present in conduction band is approximately equal to donor concentration Nd. So as donor concentration is going to be increases, number of free electrons will be more compared to holes in the valence band. So Fermi level of n-type semiconductor is now moves towards conduction band. So now Fermi level is going to be looking like this way. The Fermi level of n-type, Fermi level of n-type will be drawn over here. This is EFN. So ECN and EVN, if you say, this is, since we are relating to n-type semiconductor, ECN is going to be related to NC, which is effective number of available energy levels in conduction band. EVN, effective, it is related to effective energy levels available in the valence band, that is NV. And EFI is related to intrinsic carrier concentration. EFN is related to donor concentration. Okay, so we can calculate the majority carrier concentration in n-type, that is electron concentration, that is NN, electron concentration in n-type semiconductor. NN is approximately equal to ND, number of donors you are adding per centimeter cube, that is per unit volume. That can be calculated using this equation, NC into e power minus of ECN minus EFN divided by KT. So from this one you can write it as ND divided by NC is equal to e power minus of ECN minus EFN divided by KT. So if you simplify, at that time it will become ECN minus EFN. The meaning of ECN minus EFN is relative distance between conduction band edge of n-type and Fermi level of n-type semiconductor. Otherwise the distance of Fermi level with respect to conduction band edge. Okay, this can be written as KT natural logarithm of NC divided by ND. So if you observe, ECN is going to be related to numerator in this equation, EFN is related to denominator. So based on this one we can write equation for relative distance between any two energy levels. So we can write in this way. For example, EFN minus EFI, that is relative distance of Fermi level of n-type with respect to intrinsic Fermi level. EFN minus EFI is nothing but distance of n-type semiconductor Fermi level with respect to intrinsic Fermi level. This we can write it as KT natural logarithm of NC divided by Ni. NC is nothing but EFN, it is related to EFI is related to NI. So this equation again we are going to use in the PN junction energy band diagram. So what we have seen is nothing but we have seen about the p-type semiconductor, okay, and we have seen about the n-type semiconductor. Now we are going for the energy band diagram of energy band diagram of PN junction under open circuit. PN junction under open circuit, this we are going for the case A. B is nothing but under forward bias, C is under reverse bias, okay. And the very important point to be remembered is nothing but under open circuit PN junction will be under equilibrium state, okay. PN junction will be under equilibrium position or equilibrium condition only under open circuit. So that implies nothing but the net current flowing through the PN junction is 0, okay, as the current produced by the majority carriers is compensated by the current produced by minority carriers. That is, the current produced by majority carriers and current produced by minority carriers will be same in magnitude but opposite in direction, so that net current flowing through the open circuit PN junction will be 0 always. That is what we call it as equilibrium situation, where no current is going to be established, okay. So if you are going for the under equilibrium situation, under equilibrium condition, Fermi level of p-type and n-type will be at the same energy level. So this is very important statement that we are going to start energy band diagram of PN junction under open circuit. So the statement is, under equilibrium condition the Fermi level is constant throughout the PN junction. Throughout the PN junction it is Fermi level is constant under equilibrium condition. That means Fermi level on p side region and Fermi level on n side region will be at the same energy level. Fermi level at p side is going to be at the same energy level as Fermi level of n side. This is going to be true only in equilibrium situation, and equilibrium condition or situation exists under open circuit condition only, okay. So from this point onwards we can start the energy band diagram. It is very easy to draw. Every PN junction will be consisting of a depletion region. The depletion region is also called as potential barrier, which will be having two parameters, important one is width of potential barrier, the other is height of potential barrier. Under open circuit, let us say this is the width of potential barrier, okay. So width of potential barrier I am drawing in this way. This is width of potential barrier, under open circuit, and left of this one is nothing but p-type semiconductor and right of this one is nothing but n-type semiconductor. And just now we are going to stated that Fermi level on p side and Fermi level on n side are going to be same, so that this is the statement we are going with. This is Fermi level on p side and it is Fermi level on n side. So this I am writing it as EFN and it is EFP. Both are at the same energy level, so that we are drawing a horizontal line from the p side to n side, okay. And now we will draw it towards the p side, later will come for the n side. We know for the p-type semiconductor Fermi level is more near to valence band edge. Fermi level is more near to valence band edge, so that this will be looks like this one. This is valence band edge of p-type, and valence band edge, if it is conduction band edge, is going to be always above that one, so that this you can write it as conduction band edge, ECP. Okay, so above this ECP is nothing but simply it is conduction band, simply it is conduction band till this point. Okay, and below this EVP it is nothing but valence band. So this is valence band, and between ECP and EVP it is forbidden band. No electron can able to stay in that energy levels. Okay, and if you are going to draw intrinsic Fermi level also, intrinsic Fermi level will be in the exactly middle of ECP and EVP. Okay, this is EFI. Now width of potential barrier. Now we will go for the energy band diagram of N side. Energy band diagram of N side. If you observe this Fermi level of N side, which is more near to conduction band edge, so that we can draw over here. We will draw energy band diagram. N side Fermi level is going to be more near to conduction band edge, so that I am writing it as ECN, conduction band of N type, and above this one it is going to be treated as conduction band. So this is conduction band, and if it is conduction band, valence band will be very much below of this one, so it is EVN, and below this one it is going to be treated as valence band, and this will become intrinsic semiconductor, intrinsic Fermi level, EFI. So now we will define height of potential barrier. Height of potential barrier, okay, can be defined whenever under open circuit. We know that when majority charge carriers flows from one side to other side, as well as minority carriers also flows from one side to other side. Say for example, we are going with a hole is moving from P to N side. Okay, hole is going to be moving from P to N side, as well as electron is going to be moving from N to P side. This is the meaning of movement of majority charge carrier. Electron will move from N to P and hole will move from P to N for the majority carriers. So what is the meaning of electron is moving from N to P side? If you understand this meaning, at that time it is very easy to define height of potential barrier. Okay, so if you observe, electron is nothing but always it is free electron. Electron is nothing but, the meaning of electron is nothing but always it is free electron. So free electron is always present in the conduction band only. It doesn't present in any other places. So free electrons only exist in conduction band. If free electron is moving from N to P, the meaning is nothing but, you can draw in this way. Okay, a free electron is going to be moving from conduction band of N side to conduction band of N side to conduction band of P side. Conduction band of P side. This is the meaning. If an electron is moving from N to P, the meaning is nothing but a free electron which is only present in conduction band. So a free electron is moving from conduction band of N type to conduction band of P type. Say an electron, free electron can stay in the conduction band, at most it may stay in the lowest energy level. So say this is going to be the electron. Electron from the conduction band of N side, if it has to move towards P side, it should stay within the conduction band of P side only. The lowest energy level it can stay is nothing but this one. This is the lowest energy level it can stay. So an electron is moving from conduction band of N type to conduction band of P type is nothing but simply it is jumping from ECN towards ECP, because ECP is higher than ECN. Okay, so this difference, if you observe, this difference is going to be treated as height of potential barrier. So the electron must get this much energy such that it can able to jump from ECN to ECP. okay, then only that free electron can able to contribute for the current. Okay, so this is going to be called as height of potential barrier, which is nothing but ECP minus ECN. Similarly, a hole is moving from P to N side is nothing but a hole is moving from, hole is always present in valence band of P side to valence band of N side. Hole is moving from P to N, meaning is nothing but a hole is moving from valence band of P type to valence band of N type. So hole is going to be present at a higher value of EVP, and if it is coming towards N side, at that time it may be available at the highest energy level of valence band as EVN. It looks like hole is going to be moving down, so that is nothing but it is falling. Okay, hole is going to be looks like falling, but actually there is no hole moves. Okay, always valence electrons will move within the valence band, that will create, okay, that will be looks like a hole is moving in opposite direction. So that strictly what's going to happen is nothing but an electron, okay, a valence electron. So here a valence electron, I am going with this one, this is going to be a valence electron. Red color is nothing but valence electron, because electron present in valence band. A valence electron moves from valence band of N side to valence band of P side. So now electron is going to be moving from N to P, valence electron, that looks like hole is moving in opposite direction. So this is valence electron. So a hole is moving from P to N is nothing but a valence electron is moving from valence band of N type to valence band of P type. So again the valence electron has to jump from EVN to EVP. Okay, so again if you are going to draw this one, this can be treated as, it is going to be height of potential barrier, which can be written as EVP minus EVN. This is what height of potential barrier. Since ECP, EVP are going to be constants for P side, and ECN, EVN are going to be constants for the N side. Okay, their middles also constant, that is nothing but EFI. Okay, on P side as well as EFI on the N side is also a constant. So the difference between ECP and ECN will be same as EVP and EVN will be same as EFI of P side to EFI of N side. So this is also treated as height of potential barrier. So height of potential barrier can be defined like this. Height of potential barrier can be defined, okay, here it is ECP minus ECN, otherwise EVP minus EVN, otherwise you can also write it as EFI on P side minus EFI on N side. That you can write it as, okay, EFI on P side is nothing but this one, and EFI on N side is nothing but this one. Since EFP and EFN are going to be equal under open circuit, we can say like this, this is what E1 for example, and it is what E2. Okay, E1 is the relative distance between intrinsic Fermi level and Fermi level of P side, and E1, E2, this is E2 is nothing but relative distance of Fermi level of N side to intrinsic Fermi level. So potential barrier height can also be defined as E1 plus E2, E1 plus E2, E1 plus E2, where E1 is nothing but we can write it as EFI minus EFP. So already we have seen these equations. So height of potential barrier under open circuit is E0, and that we are writing it as E1 plus E2, where E1 is nothing but EFI minus EFP P, which already we have seen the equation for this one, KT ln Na divided by Ni, and E2 is nothing but relative distance between Fermi level of n-type with respect to Fermi level of intrinsic Fermi level. So this can be written as KT natural logarithm of Nd divided by Ni. So height of potential barrier is nothing but E0. E0 is nothing but E1 plus E2. From that one we can say it as KT natural logarithm of Na by Ni plus KT natural logarithm of Nd by Ni. So if you simplify this one, what you are going to get is nothing but KT natural logarithm of Na Nd divided by Ni square. That is what E0 you will get. So E0 is equal to KT natural logarithm of Na Nd by Ni square. So this is height of potential barrier, and the units are going to be electron volts. From this equation, okay, we can write the potential barrier voltage also V0. V0 is nothing but E0 by Q. Okay, before going to write that one, we can also write E0 in other way. Okay, we can also write E0 can be expressed in other equations. The other equations can be treated in this way. So this is what we are going for the PN junction, and for that PN junction, this is P type and it is N type. So hole concentration is nothing but Pp, which is approximately equal to acceptor concentration. Electron concentration is Nn, which is approximately equal to Nd. And minority carriers in P type is nothing but electrons, that can be written as Np is equal to, which will be calculated by using mass action law, Ni square by Na. And minority carriers in N type is Pn, which can be calculated again from the mass action law, Ni square by Nd. Since we are going to consider under open circuit, we can append a suffix as not. Not implies nothing but under open circuit. So you can write the equation E0 is equal to KT natural logarithm of Na divided by Ni square divided by Nd, you can write. So by that time it can be expressed as KT natural logarithm of Na is nothing but Pp naught. Na is nothing but Pp naught divided by Ni square by Nd is nothing but Pn naught. Okay, this is one more equation to express. Pp naught is nothing but hole concentration on P side under equilibrium. Pn naught hole concentration on N side under equilibrium. Similarly, E naught can be written as KT natural logarithm of Nd divided by Ni square by Na. So this can be written as Nd is nothing but donor concentration, which is Nn naught divided by Ni square by Na is nothing but Np naught. So KT natural logarithm of Nn naught by Np naught. Nn naught is electron concentration on N side under equilibrium. Np naught electron concentration as P type on P side under equilibrium. So these are the three important equations, first one, second one and third one, related to E naught, height of potential barrier. So E naught is equal to, I am writing like this, E naught is equal to KT natural logarithm of Na Nd divided by Ni square, otherwise KT natural logarithm of Pp naught divided by Pn naught, that is equal to KT natural logarithm of Nn naught divided by Np naught. So we know that one V naught, that is nothing but potential barrier voltage, contact potential, okay, cut-in voltage. This can be written as E naught divided by Q. So E naught divided by Q is nothing but it will become KT by Q. KT by Q is nothing but you can write it as VT. VT is nothing but KT by Q, that is called as thermal voltage or temperature equivalent of voltage. VT is nothing but KT by Q or T by 11,600 or dN by mu n or dP by mu p. So VT, and except this one all others are going to be same. Na Nd divided by Ni square is equal to Vt natural logarithm of Pp naught divided by Pn naught, which is equal to Vt natural logarithm of Nn naught divided by Np naught. So this is equation for the cut-in voltage, and this equation can be expressed like this: Pp naught whole concentration on P side under equilibrium is equal to Pn naught into e power V naught by Vt, and Nn naught is equal to Np naught into e power V naught divided by Vt. These are the important relations with respect to open circuit PN junction. Now we will discuss about energy band diagram of PN junction under forward bias. And last time what we have seen is nothing but energy band diagram of PN junction under open circuit. The important point is, under open circuit there is a equilibrium situation found, but there is no equilibrium is going to be established under forward bias. So as there is no equilibrium situation, no equilibrium is going to be established. Whenever no equilibrium is established, at that time net current will not be zero, and by that time Fermi level of P side is not going to be same as Fermi level of N side. Under open circuit there is a equilibrium established. By that time EFP is equal to EFN and net current is flowing through it is 0. But now EFP is not equal to EFN, so we cannot draw energy band diagram whatever the procedure we followed while drawing the open circuit condition. So here we are going with a little bit different approach. Okay, and now we know under forward bias, potential barrier reduces. Potential barrier reduces. The meaning of potential barrier reduces is nothing but height of potential barrier is reduces, as well as width of potential barrier also reduces. Width of potential barrier is also reduces. So we are taking this statement as reference while drawing the energy band diagram of PN junction under forward bias. So width of potential barrier is reducing, so we are going with a very smaller width compared to the previous one. So this is width of potential barrier. Width of potential barrier under forward bias. Compared to open circuit, it has to be small whenever you are drawing. Okay, so that now if it is potential barrier, that is width of potential barrier, this side left of this one is nothing but P type and P side, or right of this side is nothing but N side. Okay, so it's a PN junction. Now we know that one for P type it is going to be the energy band conduction band, let us say it is ECP. Whenever it is ECP, at that time there is a valence band edge EVP, and in the middle you will get EFI, and Fermi level is more near to valence band edge. So this is Fermi level related to P type semiconductor. If it is EFP, at that time we must show potential barrier height is going to reduces. Okay, potential barrier height is nothing but height of potential barrier is nothing but simply the difference between ECP and ECN. So ECP and ECN should be less. So now I am drawing in this way. This is what ECN. So height of potential barrier, if you want to observe, at that time this is E, height of potential barrier. Height of potential barrier, which is now lesser than E naught. You can observe this one. Okay, height of potential barrier is going to be reduces, which is less than E naught. And here also, if it is EVP at that time, you can write it as, okay, EVN will be below this one. So this will be EVN, and the difference is going to be treated as height of potential barrier. Height of potential barrier. Now this height of potential barrier is less than E naught. E naught is height of potential barrier under open circuit. So under forward bias, potential barrier height is reducing. Okay, and now if you draw Fermi level on n side, at that time this is a Fermi level on n side, which will be more near to conduction band edge, so that it is EFN. Now this is what the Fermi level on n side and Fermi level on p side is going to be different values, and EFN, Fermi level of n side, will be higher compared to Fermi level on p side. This is the condition for the forward bias. For forward bias, okay, Fermi level of n side will be at higher energy level than Fermi level on p side. Okay, this is a simple thing how to draw the energy band diagram under forward bias. Now we will see how to draw the energy band diagram under reverse bias. Energy band diagram under reverse bias we will write. And under reverse bias also, remember that one, no equilibrium situation is going to be established under reverse bias, so that EFP is going to be again not equal to EFN, since no equilibrium condition. Equilibrium only establishes under open circuit. No equilibrium exists. Next, and we know that one under reverse bias, okay, in reverse bias, width of potential barrier increases, and height of potential barrier also increases. So width of potential barrier increases, that we can draw in this way. This is width of potential barrier under reverse bias, you can say it is. Okay, and left of this one is p type semiconductor, p side of p-n junction, and right of this one is nothing but n side. So again we are going for the same thing. First of all, we are drawing the conduction band edge. Okay, lowest energy level of conduction band edge, which is indicated as ECN, and if it is this one, at that time definitely valence band edge will be somewhat below this one, this is ECP, and it is EVP. We are going with p type. Okay, and Fermi level is going to be more near to valence band edge, so that this will be EFP. And height of potential barrier is nothing but difference between ECP and ECN, so that now we are going to draw this one. This is what ECN, and below this one you will get it as EVN, and Fermi level will be more near to conduction band edge, so that it will be written as EFN. So now if you observe, okay, height of potential barrier is nothing but this one, the difference between ECP and ECN, height of potential barrier. Otherwise the difference between EVP and EVN. So height of potential barrier, now if you look at this one, it is going to be greater than the potential barrier height under open circuit. Okay, now if you observe this one, this is EFP, whereas it is EFN. So the Fermi level on p side will be higher compared to Fermi level on n side, EFP. is going to be greater than EFN. So this is a condition for energy band diagram of PN junction under reverse bias. Under reverse bias, Fermi level on P side is going to be at higher energy level than Fermi level on N side. And since the height is going to be very large, at that time no majority carriers can cross the junction, okay, whereas only minority carriers can cross the junction. So this is how to draw the energy band diagram under forward bias, reverse bias, and under open circuit. Thank you.